So today we're going to be solving systems of equations with elimination that are a little more complex than what we've seen before. And so let's start out with kind of where we left off last time. And we have two equations where the variables are lined up. I have x, then y on the left, and I have my constants on the right. So I don't need to worry about reorganizing the equation. I just need to worry about finding the least common multiple between either 3 and 64, or the least common multiple between 3 and 8. Well, most of us are going to go for the least common multiple between 3 and 8 because that's a 24. I know that the least common multiple between 3 and 64 is going to be 192. Yeah, we're going to go for the 24. So what do I multiply 3 by to get 24? I'm going to go ahead and I'm going to multiply it. And I'm going to do this in green. 3 times 8 is going to give me 24. And on the second equation, I'm going to multiply 8 times 3 to get me 24. The signs are already opposite, so I don't need to worry about making one of these negative. I'm just going to multiply by an 8 and a 3. And so my top equation is going to give me a 24x minus 24y equals, let's see, 36 times 8 is going to give us 288. 64 times 3 is going to give us 192x plus 24y is equal to, let's see, 48 times 3 is going to give us 144. Boom. And so now what we look at is when we go ahead and we combine these, our y's are going to cancel out. And we're going to be left with, let's see, this is 216x equals, let's see, that's going to give us a 2, 3, 4, negative 432. And then in this case, we're just going to go ahead and solve this by dividing by 216. And we get x equals negative 2. There's our first answer. And we know that once we get our first answer, we're going to go ahead and plug it into one of these. I'm going to plug it into the top one because those look like smaller numbers. We're going to see what we get. So we get 3 minus 3y equals negative 36. And I'm going to plug in a negative 2 for my x. 6 minus 3y. We're going to go ahead and we're going to add our 6. And then we're going to divide by negative 3. Which is going to go ahead and give us y is equal to a positive 10. So we know that we have a solution, negative 2, comma, 10. Perfect. And so these two lines cross at the point negative 2, comma, 10. So, and then one of the common things that we see is that the equations don't need to be in standard form. We've only seen standard form up until this point, but with this, the variables are in the same order. I have y on the left, and I have an x, then a number on the right. It doesn't matter that it's not in standard form where we have x, then y equals a number. You can have them in whatever form you want. It does not matter. So we're going to look for the least common multiple between either 2 and 8, which is going to be 8, or between 64 and 10, which, to the best of my knowledge, is going to be, I believe, 320. We're going to go with the 8. So I actually don't need to modify the top equation at all. It's already at a negative 8. So what I want to do is I want to somehow multiply this bottom equation to get a positive 8. Well, 2 times what gives me, negative 2 times what gives me positive 8? Well, negative 4. So I'm not going to touch the top equation. I'm going to multiply everything on the bottom equation by negative 4. So So I get a positive 8y, I get a positive 40x, and I get a positive 160. And now when I combine these, my y's cancel out. Now I want you to be careful here because we notice that the y's cancel out. Oftentimes students will move the equal sign so that when we combine these and we get a negative 24x and we get a negative 24, they'll move the equal sign in between the x and the number. Remember, both the x and the constant are still on the right-hand side of the equation, so the equal sign remains right here. There is a 0 over there. Don't forget about the hidden 0. That's a very common mistake that a lot of students make. Just make sure that it's not one of us that does that. Once we do that, we go through the process of isolating the variable. 24x is positive 24. We divide by negative 24. We get negative 1 is equal to x. Cool. And then we take that, we can plug that into whatever equation we want. I'm going to plug it into, in this case, the bottom equation. So negative 2y equals negative 10 times negative 1 minus 40. So negative 2y is 10 minus 40. 2y is negative 30. And divide by negative 2. Y is 15. And so we have a solution, a point where the lines cross at negative 1 comma 15. Perfect. And so we notice now that the equations, it doesn't matter what order they're in as long as they are in the same order. But what happens if, for instance, they are not in the same order? Well, all we need to do is rearrange the equations a little bit. And it doesn't matter which order you put them in, but let's go ahead and take a look. Now I have an equation, x, y equals a number. This is an x equals a number y. So what I want it to be in is I want it to be an x, y equals a number. I'm going to put it in the form of the top equation, which means I need to relocate that 5y. And so I'm going to copy down the top equation, negative 4x plus 4y is negative 72. And I'm going to move that 5y across so it will become a negative 5y. The 20x hasn't moved, it stays positive. The 165 hasn't moved, it stays positive. But because the 5, I changed it to the other side, it changes signs. And this allows us to either look at least common multiple of 20 or the least common multiple of 20. Well, I'm going to go with the x's simply because that's already a 20. I know I don't need to do anything fancy to the bottom one. It's positive 20. I need this to be a negative 20, which means I multiply the entire equation by 5. So negative 20x plus 20y is, let's see, 72 times 5 is going to give us 360. Cool. And now when we add these together, my x's conveniently cancel out. We have 15y is equal to, let's see, 360. That's going to be 200. It's going to be negative 195 if I did my math correctly. Let's double check. Let's see, 360 minus 165. Yes, negative 195. And then we're going to take that and we're going to divide it by 15, which is going to be 13. So y is equal to negative 13. And we're just going to take that and plug that into either equation. We're going to plug it into this bottom one because the x is already partially isolated it means that I might have to do a little less work. 65 plus 5 times negative 13. 20x and then at this stage we divide by 20. We get x is equal to 5. And so we find out that the solution to our system is at 5, negative 13. There we go. And so now that you've seen what happens when we have to reorganize the patterns, I want you guys to take a pause, look at number 7, see if you can't do it yourself, and then resume the video to see how you did. Okay, so let's take a look. I have y equals x minus 136 and x equals y minus 238. I'm going to go ahead and I'm going to resume the default x, y equals a number, which means I'm going to move this x to the left and that y to the left. I'm going to rewrite my two equations. Negative 4y. Well, apparently I'm rewriting this in y comma x. So let's turn that into a y and let's turn that into an x simply because I've already written the 4y. My positive 16x becomes negative 16x. That stays the same because it didn't move. I move that over so that becomes a negative 7y. 28x doesn't change, neither does the 238. And so now we're going to look at either the least common multiple of 28, or we're going to look at the least common multiple of, let's see, that's probably going to be 80. I'm not 100% certain. Let's see, 80 divided by 28. Nope. Okay, so this one's most likely going to be 16 times 28 divided by 4. This one's going to be 112. Just because that took so long to figure out what the least common multiple was, let's go ahead and go with the 28. It's a little easier to figure out. And now, some of you might be looking and saying, oh, hey, I noticed that all 4 of these are divisible by 4, or all 3 of these are divisible by 7. Can I instead not go for a positive? Can I reduce these to make my numbers a little easier? And yes, you can. So I'm going to work it this way first, and then I'm going to show you a shorter way by reducing the problem. So this is going to give me, oh, sorry, I need to get times 7 and times negative 4. So if I multiply that by 7, I get negative 28y. 16 times 7 is going to give me 112. And then 136 times 7 is going to give me 952. This is going to give me a positive 28y. Let's see, 28 times 4 is going to give me a positive 112. And then 238 times 4 is going to give me a positive 952. Some of you might notice that all of these terms cancel out, and I'm left with the fact that 0 equals 0, which means these are the same line. And so if these are the same line, how many times does the line touch itself? Infinitely many. And there we go. And for those of you who are thinking about, could I solve this by reducing? Well, yes. What happens if instead I divide by 4 and I divide by 7? could I do that? Well, yeah. If I divided this by 4, I'd get a negative y minus 4x equals negative, let's see, 136 divided by 4 is going to give me 34. Divided by 7, negative y minus 4x equals negative 34. We notice that again, these are the same line, which in both cases means that there are infinitely many solutions. And there we go. So today what we're going to be doing is we're going to be graphing quadratics in vertex form. Now, this is going to be very similar to how we've graphed absolute value functions in the past. So we've put down a repetition of the rules that we discovered when we were graphing absolute value. Left and right are adding or subtracting inside the parentheses. So if we ever have any parentheses, it's going to be what's inside. That's a left or right motion. Nothing there. That's a left or right motion. Adding or subtracting outside the parentheses is going to be an up or down motion, which is what we're going to see with something like this. Outside the parentheses, that's going to be up or down. Stretching and compressing. Now, we talked about with absolute value, the slope to the right. Now, stretching or compressing is going to be that same concept, but with a quadratic, because it's a curve, the slope is going to operate a little differently. But we're going to see what happens when we have things like multiplied outside. These are both going to be stretched. These are both going to be compressed. Likewise, if that was a 2x line, that line goes from a diagonal to a much steeper diagonal. That's thought of as stretching the line. If this were a diagonal, that 1/2 means that its run is going to be longer. We can think of that as compressing the line. So those are stretching and compressing. And then the last that we're going to be doing is we're going to be flipping it, changing the sign on the outside like this. All that does is it turns the graph upside down. So let's go ahead and let's get started on a few of these. Now with this is our parent graph of a quadratic function. So we're going to build ourselves a table just to see what the parent graph looks like. So if I have, let's pick some values. Let's say negative 2 to 2. Just to see where we get. And now if we plug these values in, I'm going to say, okay, so negative 2 squared, negative 1 squared, 0 squared, 1 squared, and 2 squared. That's going to give me 4, 1, 0, 1, and 4. And this is going to be the general shape of our parent function. So what I'm going to do is I'm going to graph 0, 0, negative 1, 1, negative 2, 4, 1, 1, 2, 4. And we see that it kind of makes something like a V, but in this case, it's not a complete V. It's actually a curve. And this curve we call a parabola because it's very, very steep, and as it gets closer to the vertex, it starts to flatten out until at this point, we're dealing with a completely flat line. Then it bends back up on itself. So that is the parent function. So y equals x squared. There we go. So we're going to be distorting this graph by moving it left and right, up and down, stretching or compressing it, or flipping it. So let's see what happens to our first set. So what we recognize in here is that this -1 inside the parentheses is going to mean adding or subtracting inside is a left or right motion. Because we are subtracting 1, that means we are moving to the right. So I'm going to go ahead and I'm going to graph my parent function with the points that we just graphed, and we're going to move it. So this is my parent. And what we're going to do is we're going to move each one of these points to the right by 1. So I'm going to move this point to the right. This point is moved to the right. My vertex, that point, and that point. So we have a new parabola that, as we can see, has been shifted slightly to the right of where we were before. And this is my y equals x minus 1 squared. Now, some of you might say, well, that's all well and dandy, but I want to check to see, can I actually do that? And we can. If we were to actually build an xy table, we would come up with these points. So you can either plug in these values, or I'm going to plug in my new x values and see if I end up with those 5. So it looks like I have a value at negative 1, 0, 1, 2, and 3. And I'm going to plug all these in to this right here. So negative 1 minus 1 squared, 0 minus 1 squared, 1 minus 1 squared, 2 minus 1 squared, and 3 minus 1 squared. We know that negative 1 minus 1 is negative 2. Negative 2 squared is 4. 0 minus 1 is negative 1. Negative 1 squared is 1. 1 minus 1 is 0. 0 times 0 is 0. 2 minus 1 is 1. 1 squared is 1. 3 minus 1 is 2. 2 squared is 4. So let's see if these points coordinate with our new red graph. And so I have negative 1, comma 4. That point checks out. 0, comma 1. That point checks out. 1, comma 0. 2, comma 1. And 3, comma 4. So each one of my points on my new parabola, just because I knew to shift it to the right by 1 unit, all worked out when we check it mathematically. So we know that this is a good rule for left and right motion. So next up, we're going to try some up or down motion. We know this, a minus on the outside, is going to be a downward shift. So I'm going to take my parent function, which existed right here, curve it through. There we go. I have my parent. I'm going to take each one of those points and shift it down by 3. So 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. And so it looks like my new function is down here. So y equals x squared minus 3. And if you're doubting yourself, or if you just straight up forget these rules, you can always check your work, or you can always just graph it from scratch. Now, I'm going to pick, because my x values haven't changed, so I'm going to test the same points. Realistically, if like the question before, you don't know the points have shifted, you just test negative 2 to 2, graph those points, and you'd notice the fact that you'd have a point way up here on the left. So I couldn't actually graph negative 3 on here. And I would stop right here. I might want to have included 3 after the fact. So let's plug them in. So if I plug in negative 2 squared, negative 1 squared, 0 squared, 1 squared, and 2 squared. And I subtract 3 from each one of them. Negative 2 squared is 4, minus 3 is 1. Negative 1 squared is 1, minus 3 is negative 2. 0 squared is 0, minus 3 is negative 3. 1 squared is 1 minus 3, which is negative 2. And 2 squared is 4 minus 3, which is 1. So let's check to see if these coordinates are on our new red graph. So negative 2, comma 1, that checks out. Negative 1, negative 2, that checks out. 0, negative 3 checks out. 1, negative 2 checks out. And 2, 1 checks out. All 5 of these points check out simply because we knew to just move the graph down by 3. So let's try something with stretch or compress. Now we talked a little bit about the fact that with an absolute value, this is the slope to the right, meaning we'd go up 2 over 1. And that's kind of going to be the thing. The higher the slope, the steeper the graph gets, the more vertical that v went. That quadratic is also going to bend a little farther up. Pardon my excellent animations there. So with this 2x, what we're going to do is we're going to know the fact that our parent graph is going to be stretched. And a quick way to do this, if this is our parent, is I'm going to take, okay, so this is doubled. So each one of these y values, I'm going to double them. So I'm going to say double 0 is 0. Double 1 is 2. Double 1 is 2. Double 4 is 8. This is actually off my graph. And this is off my graph. So if I really wanted to show this, I'd actually have to squish the graph in order to show that the graph has stretched. Let's take a look at what this looks like. Curve it through. There we go. And so we notice that the graph that was wider and shorter is now getting a little taller and skinnier. It looks like somebody has quite literally pulled on the graph. And so let's test out some of these points to make sure that we can actually do that. And if I have my new y equals 2x squared, if I plug in -2, I'm going to do order of operations, so exponents first. So -2 squared is 4 times 2 is 8. Yeah, that's the graph. That's the point that's off my graph. -1 squared is 1 times 2 is 2. That checks out. 0 squared is 0 times 2 is 0. That checks out. 1 squared is 1 times 2 is 2. That checks out. 2 squared is 4 times 2 is 8, and that's my last point that's off the graph. So again, all 5 of those points check out because we realize that this was a stretch, which means the y's get multiplied times 2. I'm not going to put y x2, I'm going to put y parentheses 2. So let's try one that's not a stretch, but a compression. In fact, I want to take a pause. I'm going to pause the video. Try and see if you can figure out what we're going to do with this 1/2, and then resume the video once you're done and see how you did. Okay. So what we know is that we're going to be manipulating our parent function with our starting points right here. And so we have our parent, which is right there in blue. We know the fact that this is going to be a compression, which means our y is actually going to be multiplied by 1/2. We're going to take all those y values and squish it. So I'm going to take this 4 and I'm going to multiply it by 1/2, which is 2. The 1 is 1/2, 0, 0. This 1 is 1/2, and this 4 is 2, which is going to lead me to something that looks kind of like this. Now we notice that this blue graph, in order to make it fit, would have to be squished downward. So y equals 1/2 x squared. So let's see how good we were by checking our work. 2, -1, 0, 1, and 2. So I'm going to take 1/2 times each one of these. Squared, -1 squared, 0 squared, 1 squared, and 2 squared. We know -2 squared is 4. Half of 4 is 2. So that one checks out. -1 squared is 1 times 1/2 is 1/2. So that one checks out. 0 squared is 0. Half of 0 is 0. That checks out. 1 squared is 1. Half of 1 is 1/2. That one checks out. And then 2 squared is 4. Half of 4 is 2. and all 5 points check out. So we know that we can either do it from hand, or we can remember that multiplied outside is either going to be a stretch if it's bigger than 1, or a compression if it's smaller than 1. So this is going to be the last one that we're going to do. So pause the video real quick, give this a shot, resume it when you're done, and see how you did. Okay, let's see how it worked. So it looks like I have two transformations. I have a +1, which means we're going to be moving to the left, and I have a -2 on the outside, which means we're going to be moving down. So when I graph my parent function, I'm going to take each one of these points and move it left and down. So I'm going to take my point right here, move it left 1, down 2. Take this point, move it left 1, down 2. My origin, left 1, down 2. My next point, left 1, down 2. And my last point, left 1, and down 2. And if I connect all these points with a nice curved parabola, we see the fact that this graph has definitely been shifted to the left and downward. So we're going to label this as y equals x plus 1 squared minus 2. Perfect. And so if we check our work, let's go ahead and double check. If I plug in -2, -1, 0, 1, and 2. If I plug in -2 plus 1, -1 plus 1, 0 plus 1, 1 plus 1, and 2 plus 1 squared all the way up, -2. See, -2 plus 1 is -1, squared is 1, -2 is -1. So -2, comma -1, that checks out. -1 plus 1 is 0, squared is 0, -2 is -2. So -1, -2, that checks out. 0 plus 1 is 1, 1 squared is 1, -2 is -1, that checks out. 2 squared is 4, -2 is 2, so 1, 2. That checks out. 3 squared is 9, -2 is 7. I don't have a point right over here, but I bet you that would check out. The only point I haven't checked out is -1, -2, -3. So I'm going to check out, see what happens when I plug in -3. And I'm hoping to get 2. So -3 plus 1 is -2, squared is 4. 4 minus 2 is 2. Yep, they all check out. And there we go. So today we're going to be graphing quadratics in factored form. And the idea is that factored form is going to give us the two zeros, the two factors, or the two roots of the equation. And this is going to be different than vertex form because the vertex is found directly between these two roots. And this is based off something called the zero product property. The zero product property says that if this is 0, I don't care what's over here because the whole thing is going to be 0. And likewise, if this factor equals 0, I don't care what's over here because 0 times whatever is still going to be 0. So that's what makes this special. And so I know that if I want my y value to be 0, I only need one or the other to be 0. So that's going to allow me to find what I call my root 1 and my root 2. My root 1 is simply x minus 1. If that equals 0, then it doesn't matter what's over here. So I add my 1 to both sides. I found my first root. So I'm going to plug in a nice point at x equals 1. For my root 2, I say, okay, so x minus 3 is equal to 0. Add 3 to both sides. I get x equals 3. Boom. And so now what I'm looking at is I know that my quadratic is either going to curve down through those points or up through those points. And it could be a really steep up and go very high, or it could just be a little up and be relatively flat. We don't know. So what we're going to need to do is we need to find where the vertex is, which we know is found directly between the two roots. So I'm going to ask myself, what's directly between 1 and 3? Well, 2. And so 2 is what we actually call our axis of symmetry. And that just means that what's on the left is a mirror image of what's on the right. So my axis of symmetry is x is equal to 2. So I just need to know where along this axis my vertex is going to be somewhere. It might be through this part, it might be through farther down, it might be through somewhere up. So what I'm going to do is I'm going to plug x equals 2 into my equation to find where that graph is. And so I say, okay, to find the vertex, I plug in f of 2. And that's going to equal -1, -3. I'm going to plug my 2 into both spots where there's an x. So 2 minus 1 is going to give me a 1. 2 minus 3 is -1. 1 times -1 is -1. So my vertex is at 2, -1. So 2, -1. Boom. So I have my graph. Now, we know that when we curve it through, you could graph some more points, but realistically speaking, we know the minimum height, we know the 2 zeros. The only thing is we could find is the y-intercept, and we'll find that out at a later date. So as long as you can graph the 2 zeros, the 2 roots, and the vertex, we're good on graphing quadratics in factored form. So let's try one more. We notice that this one has a negative sign out front. So will that mess up our answers? No. For root 1, I'm going to say x plus 1 is equal to 0. For root 2, x plus 3 is equal to 0. Because I know that if either one of them is 0, 0 times the other thing is going to be flat, which is going to give me some point along this line. So I have an x of -1, an x of -3. Oh, cool. So this is kind of a mirror image of what we just did. -1, -3. And so we know that the vertex is going to be somewhere between these two on this thing called the axis of symmetry. We know it repeats on each side. And so my axis of symmetry is x is -2. So what's special about that is that if my vertex exists somewhere at x equals -2, I can just plug it in. So let's go ahead and let's do that. Let's find the vertex. So f of -2 equals negative plus 1 plus 3. So -2 plus 1 and -2 plus 3. So negative, it's -1, 1. Negative times a negative is going to be a positive 1 times positive 1. We get a vertex at -2, comma 1. Oh, cool. So what we know is that the graph is going to curve up through that point and curve down back in this direction. And so that's a flipped version, and the big indicator is the fact that that negative sign, if we remember our transformations, means that the graph flips. So what I want you to do is I want you to pause the video. I want you to try number 5 and see how you do. Okay, let's give it a shot. I know my root 1 and my root 2. So if I have x minus 2 is 0 and x plus 2 is 0, that means x equals 2 and -2. So I have a point at 2 and -2. Oh. So that must mean if my vertex is directly between them, it's somewhere along this line right there. So now my axis of symmetry is at x equals 0. I just got to plug that in, see what happens. So I'm going to do that. So if I plug in f of 0, I like this because 0 is always easy to work with. 0 minus 2, 0 plus 2. Now that's going to be a -2 times a +2, which is going to be a -4. So now my coordinate for my vertex is at 0, -4. Right there. So what we have is we have a quadratic just like that. Perfect. So let's try something a little different. What happens if I don't have two complete factors? Well, it's a little deceiving because we do. I know I have one of my roots, my root 1, is going to be where x plus 4 is equal to 0. But what's going on with that? Well, I could look at it as what happens if I put that in parentheses. Well, there's my other root. So root 2 is just where -x is equal to 0. Because if either one of these is equal to 0, the entire other thing is. Which means that if x equals -4, I could plug that in. -4 plus 4 is 0. That obliterates everything. If x was 0, plug that in. -0 is 0. 0 times whatever that is, I don't even care. 0 times that is 0. So those are my two roots, at 0 and at -4. Which means that my axis of symmetry is somewhere where x is -2 again. So we're going to go ahead and we're going to plug in f of -2. So it equals a -2 times -2 plus 4. And I know a -2 is going to give me a +2. -2 plus 4 is going to give me a +2. +2 and +2 is going to give me a +4. So now my vertex is going to be found at -2, 4. 2, 4. Oh, hey. So I notice again that if I have a negative leading out front there, I know that my quadratic is going to be upside down. Yeah. Should have a steadier hand. Cool. And so these last two are what happens if we have fractions. Now, realistically with this one, I designed it a little bit more difficult than it should be, but we're going to use it and we're going to get the point across. So what we know is we know our two roots. Root 1 is where 2x plus 3 is 0, and the other one is where 4x plus 3 is 0. I know if I subtract the 3, 2x is -3. Divide by 2, x is -3 halves. I know at -3 halves, I have a root. It's not quite at 2. It's kind of in between two values. For my other root, 4x is -3. X is -3 fourths. And so this one is right there. And now what a lot of people would be tempted to do is they'd say, hey, it's going to be 1, because 1 is between those two, right? Well, remember, this is basically a quarter away from -1, and that's a half away from -1. So it's not balanced. So what we're going to have to do is we're going to have to find what is directly between those 2 points. And we do that by finding the average. Let's go ahead and figure out what the average of these 2 points are. So to find the average, what we call x bar, is we take -3/2 and we add it to -3/4, and we divide it in half. So we know the fact that these need to have a common denominator, which means that I need to have -6/4 minus 3/4 all divided by 2. So 6/4 minus 3/4 is -9/4 all divided by 2. So I'm going to keep, change, flip, -9/4 times 1/2, which is going to give me a -9/8. So that is where my axis of symmetry lies. At this really awkward value of -9/8. It's not pretty, but it works. Now, somewhere along that line is going to be my vertex. So I'm going to plug that in and say, to find my vertex, I'm going to take f of -9/8 equals 2 plus 3, 4 plus 3. And we see that this is going to get a little dirty. That's okay. -9/8, -9/8. So our first step is we're going to multiply this. I know that that's going to turn into an 18 divided by 8, which is going to reduce because 2 divided by 8 will reduce. That'll turn that into a 4. So that'll be a -9/4 plus 3. 4 divided by 8 is going to be 1/2, so it's going to turn that into a 2. So -9/2 plus 3. I'll come up over here into this box to give me some room. I know that to add these two, I need them to be common. So that's going to be a -9/4 plus, well, if I turn 3 into a fourth, that's going to be 12/4. And over here, if I turn 3 into a half, that's going to be -9/2 plus 6/2. So getting these together, I have 3/4 times -3/4, which is going to give me a -9/8. So my f of -9/8, -9/8. Well, that's an interesting vertex. -9/8, -9/8. That's a very skinny vertex. Like I said, the only thing that we probably could find after this is where the y-intercept is. That might be an important point. But as of right now, we're just focusing on graphing these 2 points and graphing the vertex to find that curve. We know this is a very skinny parabola. This new piece of information of finding the mean, finding that middle piece, is the only new part. So what I want you to do, last one isn't quite as dirty. Pause the video, see if you can solve it, unpause it when you're done. Okay. So if I find root 1 and root 2, root 1 is at 2x minus 3 is 0. This one is 2x plus 3 is 0. So I add 3 and divide by 2. Subtract 3 and divide by 2. Boop, boop. So I know I have, let's see, 3/2, which is about 1.5, and -3/2, which is -1.5. Well, I know those are on opposite sides of my origin line, or my y-axis. So my axis of symmetry is where x is equal to 0. But just in case, let's say it was an example like this. How do I find the mean or the average? Well, I know that my x bar is 3/2 plus a -3/2, all divided by 2. And this is much simpler. We know that 3 halves minus 3 halves is going to be a 0 divided by 2, which is a 0. So that's an easy way to figure out this if it looks like it's going to be a little difficult to solve. So to find my vertex, I just plug it in. So f of 0, which we always like because zeros work really well. 2 times 0 minus 3 times 2 times 0 plus 3. 2 times 0 cancels out, so it's just going to be a negative 3 times positive 3, or negative 9. That was much easier. And so unfortunately I didn't draw this to scale, so I can't fit a negative 9 on here. So what I'm going to have to do is I'm going to have to go ahead, my x's have to be by 1s because I've already plotted those points, but I'm going to draw my y by 2s. That's going to allow me to stick 2, 4, 6, 8, 9. So what we get is we get a quadratic that looks like that. There we go. So what we're working on today is graphing a quadratic in standard form. Now, this is typically done because quadratics are going to come in this simplified format. We're not going to see them in factored form or vertex form too terribly often. So we need to know how to work with this, and there's a couple different ways. You can either A, learn a couple different formula on where we find the vertex and how we find the roots and things like that. I like to see, can we factor this equation? Because we're going to learn about something called the quadratic equation later on, but most of these are going to be easily hand factored. So we're going to pull out an old trick that we have where we're going to factor this into the 2 roots. Our first trick is we take the first and the last numbers and we multiply them together. So I have a 1 times a 3, which is going to give me a 3. And because that's a positive 3, I know I'm going to be finding the sum. And then what I do is I take a list of all possible factors of 3, which the only one I have is 1 times 3. And I'm going to see which set of factors add up to a 4. And like I said, conveniently speaking, this one does add up to 4. So I'm going to be able to rewrite this expression as an x squared minus 1x minus 3x plus 3. What I've done is I've split the 4 into 2 terms. And what this allows me to do is this allows me to move forward and pull out my GCFs. Pull out GCF of x and of negative 3. Anytime I have a negative leading coefficient, I'm going to pull it out with it, which means that if I pull out an x and a negative 3, so I have x squared divided by x, negative 1x divided by x, negative 3x divided by x, so that's x, and then minus 1. And what we notice is that both terms, now that I've plotted the GCF, both share an x minus 1. So I'm going to factor that out, x minus 1 times x minus 3. And this is really what I'm after, is this piece right here. Because as we've seen previously, these 2 factors allow us to graph our quadratic. I know that I'm going to have a point at 1, and I know I'm going to have a point at 3. If you don't remember how that happened, well, we took 2 roots. We said root 1 was when x minus 1 was equal to 0, which we add 1 to both sides. There's our first root. And for our second root, we know that we took x minus 3 and set that equal to 0. Add 3 to both sides, and I get my other root. So root 1, root 2. The second thing that we went over was we said, hey, if I found my 2 roots, my vertex, that maximum or minimum point, is going to be directly between them. And I know that's going to happen somewhere at x equals 2. I don't know how high, I don't know how low. The only way to actually find that out is to take my x equals 2 and plug it in. So I'm going to plug in f of 2 equals squared minus 4 I'm going to plug a 2 wherever I see an x. And then I'm just going to go ahead and solve it. So 4 minus 8 plus 3. 4 minus 8 is going to be negative 4 plus 3 is going to be negative 1. And that's actually where my vertex is at 2, negative 1. And that allows me to graph that right there. Now the cool thing is I could have plugged it into this as well. If I plugged in a 2, that would be 2 minus 1. 2 minus 3 would be negative 1. So 1 times negative 1 is still going to get me the same answer. So plug it into whichever one you think is easier to do. So let's try that again. For question 3, we're going to do the same thing. I'm going to take that first number and that last number, and I'm going to multiply them together. Negative 1 times negative 8 gives me a positive 8, which means I'm finding the sum of these factors. Now, this set of factors is a little larger. 1 times 8 equals 8. 2 times 4 also equals 8. 3 doesn't work, 4 doesn't work, and so we've done what I've called completing the loop. I'm going to add them up. 1 and 8 make 9, 2 and 4 make 6. And I'm looking for a set that makes 6, right there. So I'm going to split my 6 into a 2 and a 4. And we know this is because that will allow me to recombine later on and get a negative 6. And then, let's stay consistent, I'll keep with purple. To factor these things, again, if I have a negative leading coefficient, whatever I pull out is going to be negative. I have an x here and a 4 here, which means that if I have a negative x and a negative 4, it's going to change both those signs and give me an x plus 2. This is going to change both those signs and give me an x plus 2. And because those are the same, I'm going to pull out an x plus 2 and get that. And again, like we've said, this is what we're after, is we want to get an equation to where we can very easily look at what's going on. Well, if I were to solve for that, I would get a negative 2. Let's see, add the 4, that'd be a negative 4. Again, if you actually want to see it written out, root 1, root 2, x plus 2 is 0, subtract the 2, boom, negative x minus 4 is 0, negative x is 4, x is negative 4, boom, there we go. And so this time, I'm going to take that middle value, and instead of plugging in the original one, I'm going to plug it into my new equation. And I'm going to say, okay, f of, let's see, this is negative 1, negative 2, negative 3. I'm going to plug it into right here. So negative 3, negative 3. Negative 3 plus 2 is negative 1. Negative makes it a positive 3. Minus 4 is negative 1. So my f of negative 3 is positive 1. Tells me my vertex is right here. So my quadratic is going to curve just like that. Perfect. And so with this one's a little trickier. So take a second and think, how am I going to split that? How am I going to graph that and find the two roots? Well, there's no b term by the looks of it. And what we'll actually realize is there is a b term. Even though I don't see that middle x, it exists. It's just got a coefficient of 0. Because 0 times anything is 0, and I would skip writing that if I were the problem. So that tells me I'm looking for whatever 1 times negative 4 is, which is a negative 4. In this case, I'm finding the difference. I want to find a difference of 0. So 1 times 4 is 4, and 2 times 2 is 4. Well, the difference between 1 and 4 is 3, and the difference here is 0. So I'm actually going to be using the 2 and the 2. And because I'm taking the difference, they have different signs. So x squared plus 2x minus 2x. And we see that these would actually cancel out, and this would simplify down to our original question. Pull out my GCFs. I have a leading negative. This is going to give me an x plus 2, x plus 2, which means I can pull out that x plus 2 and get an x minus 2 left over. And this is what we're after. That's going to tell me that I have a root at negative 2 and a root at positive 2. I know that my vertex is going to be somewhere here in the middle. And that middle is going to be x equals 0, so I'm going to plug that into my equation. And because it's 0, I'm going to plug it into the original one again, because I know that that's going to be much easier for us to handle. Yep. Because if I plug in a 0 squared, it's literally just my last term, my con. So that will give me the ability to graph just like that. There we go. Let's try something a little more advanced. So what happens if we have, with these new problems, something where I don't have a c? Originally I didn't have that middle term, I didn't have my b, but now I don't have that constant that's just on the right. Well, these are actually going to be a little easier to work because immediately I notice that somebody has distributed an x. So I can divide out an x out of the expression, which is going to give me the thing that I seek without having to factor it any further. I just boop, boop, there we go. I have my two roots. So root 1 is where x is equal to 0, and root 2 is where x minus 4 is equal to 0, which means that x must be equal to 4. So I have those two values to plug in, which is going to look like this and this. Perfect. And if I know I have two values at 0 and at 4, I know that my axis of symmetry, or that line where my vertex is going to be right in the middle where x is equal to 2. And so all I need to do is plug in f of, I can either plug 2 into this factored form or in the top form. I'm going to plug it into the top one myself. So plug in a 2. Let's see what we get. Well, 2 squared is 4 minus 8. That is negative 4. Draw my negative sign a little bigger right there. So boom, I have a vertex right there. So I know that my graph, curve, curve, and curve. So I have f of x is equal to x squared minus 4x. Perfect. Looks like that. And as we move forward, really just what we're getting into is some other variations of it. If you have something with an actual coefficient, the process is no different. You're just going to have a larger set of numbers that you're pulling from. Also, with that larger coefficient, what we'll learn later on is that means the graph is going to be much skinnier because the graph is going to be stretched. But we'll see that from our resulting graph. So we're going to work it out with 4 times 15. So that's actually going to be 4 times 15 is going to be 60. So what I want you to do is I want you to take a pause in this video, and I want you to take factors of 60 and see if you can't finish this out, and try the next one as well. I think this is a good chance to try out our skills. Okay, so now that you've unpaused the video, let's see how you did. Well, my factors of 60 this time are quite lengthy. I got 1 and 60, 2 and 30, 3 and 20, I have 4 and 15, 5 and 12, 6 and 10. 7 doesn't work, 8 doesn't work, 9 doesn't work, 10 has completed the loop. So I know with that plus 60, I'm going to be looking at sums. So 61, 32, 23, 19, 17, and 16. Ooh, that means the last ones is what I actually needed. So I'm going to go ahead and I'm going to plug those in. I'm actually going to draw this down here so it gives me a little bit more room. So 4x squared plus 6x plus 10x plus 15. And that's going to allow me to pull out 2 GCFs. Over here it looks like a 2x. Over here it looks like a 5. So 2x plus 5. Once I divide those things out, that's going to give me a 2x plus 3, 2x plus 3, perfect, 2x plus 3. And then my other factor is going to be 2x plus 5. Awesome. And so that means that my 2 roots are going to be, I'm actually going to do that up here, root 1, is going to be where 2x plus 3 is equal to 0, and my root 2 is going to be where 2x plus 5 is equal to 0. Separate that off a little bit. So if I subtract my 3 and divide by 2, that's going to give me an x equals subtracted 3 divided by 2. If I subtract my 5 and divide by 2, I get those. So my 2 roots. Negative 3 halves, which is about 1.5, and negative 5 halves, which is right there. Awesome. And so the next thing I'm going to do is I'm going to have to find where the vertex is. And luckily for us, directly between negative 3 and negative 5 halves is going to be negative 4 halves, also known as negative 2. So let's go ahead and plug that negative 2 into our function, either up here or down here. And so I'm going to plug it into the factored form, just because I want to be different. I want to show different things. So f of equals, oops, sorry, that's a 2, and then I open my parentheses, plus 3, 2, plus 5. I'm going to plug in my negative 2. Can't really tell that right there. That's a 2 times negative 2. It's going to give me a negative 4 plus 3, negative 4 plus 5. Negative 1 times positive 1, which is negative 1. So negative 2, negative 1. Perfect. And so we notice that, again, we mentioned earlier that that 4 is going to be stretching it. This is a much tighter graph. It's not that nice spread out graph that we have right there. This is very tightly bound. So we're going to play some more around with that in a later lesson. And then the last one, this is another one of those where I'm missing that middle term. So I'm going to be looking for factors of 4 and negative 9, which is a negative 36, which in this case make a difference because of that negative sign. Means I'm going to be subtracting the 2 numbers instead of like we did up here where we added them. So I have 1 and 36, 2 and 18, 3 and 12, 4 and 9, 5 doesn't work, 6 and 6, and that completes the loop. So if I need a difference of 0, I need the same number, so I'm not even going to worry about those. I know it's going to be my 6's. So if I have a 4x squared plus 6x minus 6x minus 9, that's a good place to start. So 2x, because I have a leading negative, 3. So So 2x and negative 3. And if I divide those by 2, I get a 2x plus 3. Over here, if I change the sign, that also becomes a 2x, and that now changes to a plus 3. Hey, perfect. So I have a 2x plus 3 as one factor, and for my other factor, I have a 2x minus 3. That's cool. So I have the same thing. This is what we're going to call a conjugate. So we'll see more about conjugates later on. And so my two roots, root 1 is where 2x plus 3 is equal to 0, and root 2 is where 2x minus 3 is equal to 0. So let's see. If I subtract the 3 and divide by 2, there's 1. If I add the 3 and divide by 2, there's the other one. So I have negative 3 halves, and I have positive 3 halves. So negative 1.5 and positive 1.5. Awesome. And those look like, to me, I don't know about to you, but those look like they're on opposite sides of my y-axis. So I know that vertex is going to be somewhere where x is going to be equal to 0. So I'm going to plug 0 in up here because this looks like it might be a little more work. Not much, but a little. 4 times squared minus 9. And if I plug in that 0, well, that made that easy work. F of 0 is negative 9, which, unfortunately, on my 1-by-1 graph, I'm going to have to change things up a little bit. I've already graphed my x's, so my x is going to stay by 1s, but in order to fit my y on there, I'm going to have to make my y by 2s. So now it's 2, 4, 6, 8, 9. There we go. Perfect. And there we go.